11. We'll do that. So many. Start with 1 and go to 50. Okay. Really? Start with 1? Okay. Number 7. Okay. You have it with you? Maybe I have it here. Number 7. The ball rolls up the ramp. Okay. Okay, so there's a ramp. And a ball starts rolling up the ramp. That's pretty distracting to me when you guys are talking back there. The ball is rolling up the ramp with an initial speed v0. And it travels up the ramp a distance d before it turns around. So the highest point it gets to up the ramp is here. So this distance is d. And at that point, so the path it's going to follow, it's going to do this and then turn back around. And we need to figure out the acceleration. So I think a good place to start with problems like this is draw a picture of what's going on, draw where your 0 position is going to be, draw your positive direction, and just start to label out the positions. Okay, so I'm going to put the 0 position at this instant when it's at v sub 0. Okay, so that's the 0. And it doesn't, this is arbitrary, both of these, but I guess I'll positive direction up the ramp. And so if you start at 0 and you go a distance d in the positive direction, what's the position at that point? D. Yep, positive d. So I'm going to define my 0 position this way, my positive direction this way. My time equals 0 is going to be at that instant where the speed is v0. Oh, another thing, now that we've chosen the positive direction, what's the velocity? So we know the speed is v sub 0, but now we also know that it's a speed of v sub 0 moving in the positive direction. And so now we can say that the velocity is positive v sub 0. Okay, before we chose the positive direction, we don't know what the sign is. And what are we going to choose as our instant t? Yeah, right. So let's say that's the highest point up the ramp. And by the way, what's the velocity when it's at the highest point? 0. Yep. So it's starting out fast, it's rolling up and slowing down. It gets to this point, and that's where it goes. As it's slowing down, it's like 0.1 meters per second, 0.01 meters per second, and then it hits 0 meters per second right before it starts speeding up in the other direction. So let's list out variables and think about what we know now. So t a p sub 0, so that's the position at time 0, p at time t, v0, and velocity at time t. We're trying to find the acceleration. what do we know out of these? We don't know t. Like we know what instant that represents, but we don't know a number for it. We don't know what the stopwatch says. Do we know p sub 0, the position at time 0? We do. Yep, because so this is a picture of what's going on at time, and we put our 0 position there. So p0 is 0. It's not, that's not always true, but it's true the way we set it up. Do we know the position at time t? Yep, that's positive d. V0, well, we know that we're just calling it symbolically V0. So that's like a given number. Okay. So we know this. And do we know V0? Yep. Okay. So the three equations that we're considering are V is equal to V0 plus AT. P is equal to P0 plus V0T plus 1/2 AT squared, or 2A times the quantity P minus P0 is equal to V squared minus V0 squared. All three of these have A in them, so that's not a problem. But the top two equations both have T in it also, and we don't know what that is. This is the one that looks like it's going to work for us, the third one. So 2A times the quantity, what was that called, D? Quantity D minus 0 is equal to 0 squared minus V0 squared. And now V0 is usually a variable, but now in this case, that's a value that we're given. So we're going to get our answer in terms of this V sub 0. So 2AD is equal to, this should be squared, is equal to negative V0 squared. And now we're just solving for A. So A is equal to negative D V0 squared over 2. Not good with dividing yet. That's better. Does it make sense that the acceleration is negative? Yes, because we know from thinking about what's going to happen here, it's going to move this way, it's going to slow down. That's a positive velocity and a negative acceleration, so that makes sense. That's slowing down. And then once it turns around, it's going to speed up. It'll have a negative velocity and a negative acceleration, so that's speeding up. So yeah, that makes sense. Any questions about that one? Any other homework questions you want to see? We'll get to that. Yep, I just should not have assigned that yet. I have to talk about that today. Yep. Yes. Yeah, that's positive 9.81 meters per second squared. And then think of the sign of it as just being the direction. Number 10. Okay, so an object moves according to the acceleration function A as a function of time is equal to 2 times the cosine of 4t. And we know that at time 0, the velocity is 1 meter per second. And we want to know First, at what time between 0 and 0.75 seconds does the object change directions? And second, what's the object's position at the time it changes directions? So what's the position at that instant when it's changing directions? Given that p at time 0, well, p is equal to 5 when time is equal to 0. Okay, so this motion looks like this, where this amplitude is 2. And so this is a position versus time graph. And what physical feature of the position versus time graph tells us what direction it's moving? That's the acceleration. The direction is determined by the velocity. So we're looking for where the slope changes. Okay, so we're looking for a point like right here, where it's a negative slope, so a negative velocity all the way to here. It's getting smaller in magnitude. Right here, it has 0 velocity, and then the slope starts being positive after that. Okay, so what we want to do is look for a point where the velocity is equal to 0. Okay. So for part A, find where the velocity is equal to 0. So to do that, we're going to have to use that acceleration to find the velocity. Do we have to differentiate or integrate? Right, we have to integrate. So the velocity as a function of time is the integral of the acceleration as a function of time with respect to time. And so that's the integral. I'll pull out the constant. And we have cosine of 4t dt. And do use substitution, and you should get 1/2 sine of 4t, right? Plus c. Yeah. Okay, everyone with me there? Now we have to use the boundary condition to find the constant of integration. So the boundary condition says that at time equals 0, the velocity is 1. So that says that 1, the velocity, is equal to 1/2 times the sine of 0 plus c. Sine of 0 is 0. So this says that the constant of integration is equal to 1. And now just update our velocity function. And the velocity is 1/2 times the sine of 4t plus 1. Uh, and did any of you get to this point? Okay. So at this point, there's a issue with this problem that I need to correct. And that issue is, so now set the velocity equal to 0. So 0 is equal to 1/2 times the sine of 4t plus 1. Um, so uh, we're looking for sine of 4t is equal to -2. P-value where sine of 4t is equal to -2. There isn't one. So that doesn't make sense. Well, damn it. Okay, that's my fault. Uh, yeah. Well, um, this approach works fine. It's just that there's no answer to this. Um, what? Yeah, I mean, the problem was that I asked the question wrong. So let me and I and let so let me correct this. Okay, so um, first of all, the graph that I drew here was the function that's given. So this is really an acceleration versus time graph. Okay, and uh, so also when I was going through this, I described that wrong. Since this is acceleration versus time, um, it's not the slope that matters. Okay, um, it's the slope of the position versus time graph that matters. So what we're really okay. So now for the velocity versus time graph, we have something like this. Where it's going to be oscillating +1. So it's going to be oscillating like this, where this is a velocity equal to 1. And we're looking for where that graph is equal to 0. That doesn't happen. Okay, so I'm going to correct this problem right now, and then we'll go through it. And I'll fix that on the homework too. Okay. So number 10, the reboot. So let's say, so we know that the acceleration as a function of time is equal to 2 times the cosine of 4t. This time, let's say that at time 0, the object's velocity is, let's say, negative 0.25 meters per second. And now we'll do the same questions. So first we want to know time between 0 and 0.75 seconds does the object change directions. And second, so again, given that at time equals 0, the position is equal to 5 meters. What's the object's position when it changes directions? Okay, so what did I change? I only changed one thing. And do you see how that's going to affect the ability of us to come up with an answer to this problem? Um, I uh, yeah, so I shifted this graph from being like this to being down here. No, let's make this positive. Okay, so I didn't shift it as far now. Okay, I shifted it down to here, and now this graph is going to hit the zeros. Okay. All right, so the velocity as a function of time is equal to the integral of 2 times cosine of 4t with respect to time. And if you do that integral, you get 1/2 sine of 4t plus the constant. And now we have to use the boundary condition. We have a different boundary condition that's going to make this velocity have zeros. So the boundary condition says that when time is equal to 0, the velocity is 1 meter per second. That's the old one, 1/4, right? Okay, so 0.25 is equal to 1/2 times the sine of 4 times 0 is 0, plus c. So c is equal to 1/4. And so the velocity function is equal to 1/2 times the sine of 4t plus 0.25. And now we're looking for where the velocity is equal to 0. So 0 is equal to 1/2 times the sine of 4t plus 0.25. And so negative 0.5 is equal to the sine of 4t. And then the inverse sine, okay, so 4t is equal to the inverse sine of negative 0.5. Anytime you're doing derivatives with trigonometric functions, you need to be in radians because the chain rule doesn't work any other way. So you need to use radians to do calculus with any trigonometric functions. Okay, so divide both sides by 4, and you get time is equal to inverse sine of negative 0.5 over 4. Can someone calculate that for me? Negative something? Okay. Pi over 24. There are going to be multiple zeros, but we need one that's between 0 and 0.75 because that was given in the problem. This is in seconds. And now all we have to do is, so this is where it changes directions. Okay. Now we have to plug that into the position function and just calculate the position at this instant. We don't have the position function yet. We have to integrate again for that. So how do we get the position function from what we have? Yeah, integrate the velocity function. So position is a function of time, is the integral of the velocity with respect to time. And so that's the integral so the integral of 0. What was that? Half. 0.5 times the sine of 4t plus 1/4 integrated with respect to time. And so that is negative 1/8 times the cosine of 4t. The integral of 0.25 with respect to time is 0.25, or it is t over 4. And then plus a constant of integration. And so now we're going to use our boundary condition. And our boundary condition says that when time is equal to 0, position is equal to 5. So 5 is equal to, so when t is equal to 0, we have negative 1/8 cosine of 0. Cosine of 0 is 1, so this is negative 1/8 plus 0 plus c. And so c is equal to 41/8. And so our final answer for the position function is negative 1/8 times the cosine of 4t plus p over 4 plus 41/8. And now we just want to evaluate this position function at the instant when the object changes directions, which is t equal to pi over 24. So the position at pi over 24 is negative 1/8 times the cosine of pi over 6 plus pi over 96 plus 41/8, whatever that is. Any questions about that? Okay, so sorry about that mistake. That was my mistake. Think of it in the reboot form, and I'll correct that on the homework sheet too. Any other homework questions? Okay. So now we need to talk about relative motion. And so far, we've talked about measurements based on the location of one zero position and one positive direction. Okay, one single thing is making these measurements. So this object flies up into the air, comes back down. We decide how we're going to measure it by putting the zero position on the ground or somewhere, saying the positive direction's up, and then we have one measurement. But there could be more than one measurement of any motion. You know, you could have physicists on each side measuring it, and they don't have to make the same choices of the zero position or the positive direction. Okay, so now I want to talk about the relationships between different measurements and a way to convert from one measurement to another one. Okay, and so for a given motion, imagine the measurements are done twice. And in these two measurements, we're going to deal with a case where the positive directions are the same. So the positive directions are the same for both measurements. But the zero positions are different. Okay, so let's say that we have this object moving along a line. We're going to call this object C. And it's being measured by two people according to a zero position that we'll call A, and a second zero position that we'll call B. Okay, both of these have the same positive direction. Um, now at each instant, the object C has a position value for each 0 position. Okay, so notice that the way it's drawn here, with the positive direction going this way, according to this measurement, is that position positive or negative? Positive. And according to this one, positive or negative? Negative. So those values are not the same, even though obviously the motion's the same, they're both measuring the same thing. Okay? And we want to figure out a relationship, a mathematical relationship between those two measurements at any instant. So first we're going to use a naming convention. So we'll say that the position of the object C, and then it's like a fraction. This is like a fractional, the subscript looks like a fraction. So the position of C over A, and we're going to call this, when we talk about this, we're going to say this is the position of C relative to A. And what that means is the position of the object C measured by that 0 position we're calling A. And then the position of C relative to B, we're going to call that the position of C relative to B. And the meaning of that is that's a measurement taken from that B0 position, the object. And now the relationship between those two measured positions is the position of C relative to A is equal to the position of C relative to B plus the position of B relative to A. Okay, so this is saying, so if we want to know what you would measure in that coordinate system, that 0A, you measure what that position is in terms of B. You measure where A says that 0 at B is. So let's look back at that picture. Okay, so from A, you can measure two things, notice in this picture. You can measure a positive position for the object, and you can also measure a bigger positive position, the way I have it drawn here, for B. And if we take both of those measurements, we can do this calculation. And you know which one you're doing, let's see. So yeah, B. Okay. Let me do, Oh, okay. So to think of the, to remember the, um, this equation, here's like a memory device for this equation. Think of the subscripts as having to satisfy fraction multiplication. Um, so the subscripts always follow fraction multiplication if you have it set up right. So what I'm saying is C over A is equal to C over B times B over A. And if you have this equation set up in the wrong order, then if you think of it as fraction multiplication, it's not going to be correct, you know. And so that'll tell you that you have this organized wrong. Um, okay, so let me go up here and let's put some distances on this stuff and we'll see how this works, okay? So let's say that between A and B, there's a distance of 10 meters. And let's say that between A and C, there's a distance of 6 meters. And that means that between B and C, there's a distance of 4 meters. Okay. And let's say we want to figure out the position of this object according to A. Well, we can look at it and see um, what's the if so if we're measuring the position of that from the 0A, we know that we start at 0, go 6 meters in the positive direction. So we expect that measurement to say 6, right? What do we expect B to say about the position of object C? -4, because it's in the negative direction, right? And what do we expect A to say about the location of B? +10. Okay, so in the example above, the position of C relative to A is equal to the position of C relative to B plus the position of B relative to A. What did we say was the position of C relative to B? -4. What did we say was the position of B relative to A? So we're looking for according to A, what's the position of B? +10. And so you get an answer of +6 meters, which we knew right from the start. One thing to notice about this is for any A, B, the position of A relative to B is negative position of B relative to A. Yeah, so if you're measuring, so if you think of A and B as both treating both of those as zeros, you can measure either one of them with respect to the other one. And if you measure A with respect to B, that's just the opposite value, same magnitude, opposite sign of measuring B in using A as a coordinate system. Yeah, so a lot of times that's useful in these problems. Okay, well, um, now, what if those zeros that we're using for measurements are moving? So we're taking measurements just using like we're moving our ruler around that we're using to take these position measurements. Okay, that can happen. Like um, you could be uh, you could be measuring the position of an object while you're riding around in the back of the van, and you know your ruler is moving with the van. Okay, well, you can just take time derivatives of everything in this equation, and the same thing will work for velocity, and the same thing will work for acceleration. So the velocity of A, sorry, use the same subscripts. Velocity of C relative to A is equal to the velocity of C relative to B plus the velocity of B relative to A. And with acceleration, the acceleration of C relative to A is equal to the acceleration of C relative to B plus the acceleration of B relative to A. And again, notice that the velocity of A relative to B is equal and opposite to the velocity of B relative to A. And same thing works with acceleration. Acceleration of A relative to B is equal to the negative acceleration of B relative to A. Okay, so let's stop there. I'll do some examples next time. And yeah, see you in lab tomorrow.